Hey, everyone. For as long as I can remember, as long as I've been part of the GNU Radio community at least, people have been asking, how can we equate what my SDR is doing to an absolute power level? Like, how can I know what power I'm transmitting at? Or if I'm receiving a signal, how strong is it based on my SDR measurements? And also, going back to use RP1, people have actually been doing that, so it's definitely possible. But whenever people ask this on the mailing list or elsewhere, like, questions are sometimes evasive or vague. So today I want to sort of remove the shroud of how that actually works, how absolute power equates to what's happening inside an SDR. So to start off, I'm going to head over to my pad here to go over some fundamentals. So let's assume I have some white box which is producing a current, goes through a resistor, meaning I have a voltage here. And this is going to be my model for my software-defined radio or whatever. This is just going to be a model for now. Going back to early physics lessons, we know that the power is equal to the voltage times the current. If we have a time-dependent current and voltage, then the instantaneous power is also equal to the product of the current, the instantaneous voltage and current. We can actually remove the current in this simple case by using Ohm's law. So V squared of T over R is also a valid way to express my power. This is not yet exactly what we need. What we really need is an average power. That's what we're going to be dealing with. P equals, and then we're going to integrate as a means of averaging from 2 points in time, T1 to T2. Let's see, T2 is in the future. So 1 over T2 minus T1 will be our averaging coefficient. And then just simply put in our signal here again, V squared of T over R dt. This is a really, really important equation. I'm going to mark it in color, just because we will be needing that later. Equation number 1. To make this a little bit more, to illustrate it better, let's say V, as an example, equals a sine wave. V of t equals sine 2 pi ft. So sine wave goes 1/2. Now, physics teacher might say 1/2 watt, and the answer is also 1/2 watt because R is 1 ohm, so 1 over 1 ohm. And then the unit of this here is volts squared, so we have volts squared equals volts squared over ohms equals watts, so we have 1/2 watt. So in this case, we would have 1/2 watt of power. Now, there's something else I need to introduce real quick, and that's decibels. And for that, I'm just going to pick something that is completely unrelated to RF. Let's say we have 2 bottles of beer. And now in the process of finishing this talk, I will have to drink one of those just to get through my talk. So left with 1 bottle of beer. This guy, what does this have to do with logarithms or decibels? Well, decibels are simply a way of expressing a ratio. So I'm just going to use some different paper here. So let's say my baseline reference value is 2 bottles of beer. I'm left with 1 bottle of beer after drinking one. So I have a ratio of 1/2 because the unit cancels out. I can also express this logarithmically in decibels by taking logarithm of base 10, multiply that by 10, and this equals -3. So log 10 of 1/2 is 0.3 approximately. Multiplied by 10 is approximately -3 dB. So I've reduced my beer by -3 dB, and this is important. I used beers because I wanted to clarify that this is nothing related to power or anything like that. This is just a ratio. Reducing anything by 3 dB just means halving. However, we like to use these logarithmic units also when we're talking about RF power. So how does that work? Quite simply, let's see what happens if I try and calculate a dB value of that. So 10 times log 10 of 1/2 watt equals what? Now I can't really calculate this because I can't take the logarithm of watts, but what I can do is I can say, well, I'm going to calculate a ratio where my reference value is 1 watt. So cancel out watts, leaves us again at minus 3 dB. But because I snuck in this watt to actually make the math possible, I have to add it here again just to make sure I knew what I talked about. So minus 3 dB watts is the same as 1/2 watt, except in a logarithmic fashion. I'm going to need these logarithmic units later on, which is why I'm introducing them here. Only one last thing: dB watt is not actually a common unit we use in RF. What we prefer is a reference value of 1 milliwatt. So if we have 1/2 times 1,000 milliwatts. The milliwatts cancel out. We have 1/2. So the nice thing about logarithms is the product becomes a sum. So I can sum up the logarithm of 1/2 is minus 3 dB. 1,000 is 30 dB equals minus 27 dB milliwatt. So I'm going to start writing my milliwatt, but then I'm just going to stop after the m just because that's the convention. dBm is the logarithmic representation of power as referenced by 1 milliwatt. Okay? So that's that. Now, let's say this white box is actually a digital to analog converter. And what's feeding it is some kind of software. So this would be our SDR software, probably, or hopefully GNU Radio. Feeds into the DA converter, some bus, it doesn't matter what. In software, we can also have a sine wave. Totally, no one says we can't have a sine wave in software. In fact, we do that all the time. However, let's see what happens if I put that in my axis. So my t-axis is going to be valid in software because there's no reason I can't represent time. So this is okay, I can put a t here. But what do I put on the y-axis? Not quite clear. It can't be volts because we don't have volts in software. We don't even have this resistor in software. So it's going to complicate things further. The best we can do for now is we can just say, well, this is +1, this is -1. These are just numbers. And so my unit is unitless, basically. The other thing that's important in software is we don't have an analog quantity here. Rather, we are sampling this. So the sine wave I drew is fake, does not exist in software. What we do have are these sample values that I'm trying to draw equidistantly, unsuccessfully. 4 of them. So these 8 numbers here represent my sine wave. If I want to calculate the power of that, then I'm going to copy this equation because it's still useful, except I'm going to have to modify it. First of all, my integral becomes a sum. My signal, I'm going to call it x of k times ts, where ts is the time difference between 2 samples equals 1 over the sampling frequency. Usually we don't really write it out. So x of k, I'm using square brackets to indicate integer indices, and I'm calling it x instead of v to indicate that this is not actually a voltage. So x module squared of k divided by what? Well, this is going to be a number of points. Let's say we're going to integrate over n points with, n times ts equals t. So we say k goes from 0 to n minus 1, and then the average. So average of the square, that's going to be my equation for power on the digital side. So we have power on the left side, we have power on the right side. Obviously what we're going to try and do is put them together. One little thing about these units here. So we have dBm, which is, effectively something milliwatt on the analog side. We have an equivalent thing on the digital side as well. So if I put my sine wave in here, example, so let's say xk equals sine of 2 pi k over n, then p equals 1/2, same as here, except I don't have a unit, because I didn't have a unit here to start with, and I didn't have my resistor. So I have a unitless quantity for my power. A different signal that is very, very useful in SDR is not a sine wave, but a complex sinusoid. And the complex sinusoid, unlike the sine wave, it also has an imaginary part. So it has a sine, it has an imaginary part, a real part. E to the j blah 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 something, module thereof is always 1. So this will have a unit power, p equals 1. And if I say that +1 and -1 are also the maximum input values of my digital analog converter, then I can say, so let's write this down somehow. If x max equals 1, with reference to my DAC, then this here is actually the biggest, the largest power that I can produce on the digital side. I can't really go any higher, because then I'd exceed the input of my DAC. So this here is called the full scale power, or this here is a full scale signal. And if I do 10 times log 10 of 1, and now I need a ratio of something, so I'm just going to say, P full scale. Then I end up with 0 dB, and I'm going to call this 0 dBFS, staying in convention with what engineers do everywhere else. So 0 dBFS means this is a good proxy for the largest signal that I can put into my DAC. So we're almost done here. Clearly, if I can map, I'm just going to push this up a little bit. If I can figure out this equation where y equals, in dBFS equals x prime in dBm, then I sort of bridge the gap. That's really all I need to know to have power on the digital side, power on the analog side, and know what they are. I can, in fact, simplify this a little bit. I'm going to take another cheat sheet. Let's say this here is my digital power. This is my analog power. This here is 0 dBFS, so this is also a bound. And let's say this is x dBm. So if I'm at 0 dBFS and I have x dBm, my simplification will be that the response looks like this, where this curve has a unit gradient, meaning I go 1 dB in this direction, I also go 1 dB in this direction. Because this means that my x value is really all I need to know. So going back to my pad here, if I can figure out what 0 dBFS is in dBm, I'm basically done. This is the number. I need to solve for x, and then I'm able to translate analog and digital powers. Okay. Let's go back to the slides and see how this looks like in real life. Because the what I just said explains everything on a theoretical problem, on a theoretical level. So what's the problem? Are we done? Well, no. Because in reality, schematics look much more difficult than the one that we just put on the slide or on our pad, because that's something you only see in EE 101. In reality, you don't have 0 ohm traces, and you have amps and whatnot. Also, frequency-dependent behavior. Plus, the schematic is really just one piece of the equation. What you also need to know is what does the actual PCB look like, and the mechanics and everything, to properly calculate what's going on. This is the TwinRx daughter board schematic, or at least a simplified version thereof. And it also has frequency-dependent behavior, so that's something else we need to factor in. But what's most important is that every single component that we throw onto a PCB has a tolerance. We just don't know exactly what its capacitance is, or its amplification. which means we can never actually take a schematic and then fully map our 0 dBFS value to an X value. So, are we stuck? Like, what's our solution? Because you might think, I have a calibrated device, or at least I've seen one, and if it's a signal generator, I can tell it to produce exactly X dBm. Or if it's a receiver, it can tell me how strong my input signal was. I can do all of that. So what's the problem? Well, first of all, if you're talking about professional measurement equipment, it's designed differently from an SDR, where this calibration information is actually like one of the most important things, which is not true for SDR, where we think about low cost or size, weight, and power, stuff like that. So first of all, this is a big design criterion. And also the designers, they spend a lot more time thinking about exactly these relationships between power and how can I model that. And also, what they usually have is they throw in a lot of sensors, temperature sensors, power sensors, that feed back information. So I can have some kind of algorithm running in the device that handles my 0 dBFS to X mapping. But most importantly, they do factory calibration. So if you've seen that probably, you buy a new spectrum analyzer or something, it has a sticker on that says calibration valid until, well, on my devices it'll say October 2008 or something like that. So factory calibration is a key piece of the puzzle. And if we want to now add a absolute power knowledge mode to our SDR, then we also have to be able to calibrate that. And we have to make sure that we get that information, but we will have to use an external piece of equipment. So that's an important piece of thing. Why is that? Well, it's because we're retrofitting this whole calibration API rather than having it designed in the first place. Okay, so that's sort of like the first part. Let's talk a little bit about the new things in UHD and GNU Radio that help you do that. First of all, we have some new APIs, both in UHD and in GNU Radio. And in GNU Radio, they are available in Python and C++, and of course in GRC. For example, we can now put in absolute power levels into our USIP sink and a USIP source. UHD FFT and UHD SIGGEN GUI have been updated to use those. And I have a demo, but who cares about slides? Let's look at real stuff here. So first of all, I want to introduce the hardware that I'm using in this setup. This is my B200 Mini. I'm using this as a signal generator. It's a transmitter. X300 here is used as a receiver. Now there's a couple of things that stand out. You might say this is not approved standard operation. First of all, I took off the lid of the X300 and put on a 12 centimeter fan because it's way quieter, which is good for the video. But the main thing that stands out is I'm putting a transmitter directly into a receiver without an attenuator. That is never, ever recommended unless you're doing a presentation at GRCon on power levels. I trust the software enough to believe that this won't blow up my LNA, and let's see if I'm right. Okay, so let's go to our actual application. So this is the signal generator, and something that you can see is that here at the bottom left, I am now be able to set an actual power level. So in the past, this was just a gain value, and it's set to approximately minus 25 dBm. Now if I head over to my receiver, HDFT, I'll zoom in a little bit. This is what's running on my X300. Let's go at the peak, and it's approximately minus 25 dBm. So something's working. That's good. What's new in this application is you can see, like on the left side, the label says dBm. If I scroll down, same thing. I have an RX power reference level set to approximately minus 10 dBm. Okay, let's go back to my slide deck real quick because I have a question for you. Actually, let's go back to my application. What happens if I move this reference level slider to the right? Well, you can think about it for a sec. What does that even mean? Like I'm changing the reference level. Okay, I'm just going to put in a number here. Minus 5 is a good one. So I'm going to increase it by 5 dB. Zoom up. And what's changed? Well, nothing's really changed. Like this looks exactly the same. Is that intended? Yes, that's exactly intended. Because what this is supposed to display is the incoming power level. And remember, I did not touch the transmitter. I only touched the receiver. So changing the reference power level only changes my frame of reference, but it shouldn't actually change this here. Now if I go to the scope mode, then you'll see I'm at approximately 0.1 amplitude here. If I go back down to -10 where I was before, then I'll click scale here. You can see I've actually I've actually increased the amplitude to about 0.2. Is that expected? Yes, absolutely. Because in order to increase the power reference level, I have to decrease the gain. Because increasing the power reference level means I need more power to reach 0 dBFS. So that's that. So next question: what happens if I drag the slider to the left? Now I gave you a couple of clues, so you should be able to figure this out. But let's say I'm going to drag it down here. Actually, I'm going to type in a number, -25, and boom, what happens? Okay, first of all, this goes down. What's going on here? Also, it looks kind of jaggy. Well, that's odd. Or is it? And I look at my scope, all over the place. So what's happening? Well, the problem is I increased my gain now, and my incoming power level is clipping the ADC. So this is no longer a valid signal. I cannot do any kind of DSP on it. So I'm going to put it back just so to be safe. But as you notice, I put in -25, which is also the power of the input level. And even a theoretical perfect ADC would start clipping at that value. And this is not a perfect ADC because they don't exist. So you always want to back off a little bit. Let's go back to my spectrum here. And there we are, nice and clean again. All right. So that was my quiz. One thing to point out is that here I have a TX power, whereas here in UHD FFT I have a reference power. Why is that? Quite simple. The signal generator is a very simple application. I know that I'm transmitting a sinusoid. I know its amplitude. So in combination with the reference power level, I can now actually accurately predict the output power. So we're at like 0.5 means we're 6 dB, we're at -6 dBFS. So this application now, all it needs to do is set the reference power level to -19 approximately, and then we're done. That's it. So on the receiver side, though, it's different because we don't actually know what we're receiving. So all we can do is the reference power levels. It's the best we can do in this case. Okay, I don't really have that much time here, so I'm going to have to be brief. But like, how is the user calibrated? And the answer is we have a tool that does that for you. And effectively, what it does on the transmit side, it just transmits at a different, like a whole bunch of gains and frequencies, and then uses an external device to accurately measure what you were transmitting at and puts that in a database. On the receive direction, it's the exact same. In the opposite direction, we have a calibrated signal generator that we tell it to transmit into our device. We set different frequencies, different gains, record that. And then you end up with curves like that. Very briefly, this is the transmit response from a B200. You can see the power dropping over frequency. That's expected because everything has a low pass characteristic, and the B200 Mini, where I measured this, does not have sophisticated circuitry to sort of compensate for that. So it'll go down over frequency. It's pretty linear in the middle, and then towards the bottom, this is an interesting artifact of my power meter. My power meter was actually not sensitive enough to pick up those low powers. So eventually it sort of fizzles out, but this is not actually an artifact of the user. Our tool knows how to handle that, so we can still use that data. All right, final section of this presentation. There is actually a little bit more than that, because measuring power is not quite as simple as it looks. So I already mentioned this part here. So if you start clipping, nothing goes, everything's invalid. Back off from your 0 dB FS value, and then you'll be fine. All right, different problem here is the choice of window function. Now this is something actually I kind of cheated because I started the demo before the video. if I go back to this here, you'll see I chose a rectangular window. If I choose the Blackman-Harris window, which is the default, then two things happen. First of all, my, whoops, well, this is hard to, the side lobes go down, so the square wave looked a lot like this. However, the other thing is my main lobe is a little bit below the minus 25 dBm. And that's because the energy that's coming from the sine wave is actually distributed within these FFT bins. So this should really read dBm per FFT bin after FFT processing. It's a bit too unwieldy. That's why we leave it as it is. Here you can see what happens with different windows, and also in a rectangular window what happens when you don't exactly hit the FFT bin. Now, there's something very, very important, and I'm going to go back to my pad for that, which we need to talk about, which is you can also calculate power in the frequency domain. That's totally fine. So, looks like this. So we have two frequencies, F1, F2. We have two frequencies, F1, F2. So F2 minus F1. And now we assume we have capital V is the Fourier transform of my signal, V of F over R squared dF. This is also a valid way to calculate our power. It's called Parseval's equation. This is only inequality though if my frequency bounds are chosen such that they encompass the entire signal, same as they do with the time bounds. So going back to my slides here, what happens if I have like a different type of signal? So for example, this is an OFDM signal, the blue one is, and the red one is the same OFDM signal which I pass through an incredibly awful amplifier. So GNU Radio has blocks to model that kind of behavior. So basically I'm distorting my signal, and now all of this power is going out of the intended band. And what if the FFT, UHD FFT widget can't do is tell you like how much power is on the left and how much power is on the right, but it could. Like we could have like a feature where you do sort of a lasso select of a region, and then it sort of adds up the available power in the bins, and then you get the total power there. So these are a little bit more advanced topics of power estimation, spectral analysis. I gave a talk on spectral estimation at last year's GRCon, if you want to take a look at that. The key takeaway here is you can't just always look at that y-axis and it'll tell you the precise power. So that's it from my end. Doing absolute power related things with SDRs and GNU Radio has never been easier than it is now, especially if you're using the USRP. However, you need to know what you're doing, unfortunately, and you also need calibrated equipment if you want to repeat these experiments yourself. But if you have those things, you can just like go at it, and well, I hope someone tries it out and gives us some feedback. All right, that's that from our end. Thanks for listening, and I hope this was enlightening. Bye bye.